All right. Hi, everyone. So today we're going to get into jumping into code and starting to see like, okay, how do we fit these classic models? And, I guess the first, few lectures we were saying, hey, we're not actually going to be working with these models. And I was thinking about it today as I was coming in, and that's absolutely not true. We are completely working with these models. It's just that we are working, we think of these as the hidden process. This is the thing we don't see, and we are trying to estimate that thing. So there's going to be a layer between us and this hidden process. And that process could be like observation error, or it could be that the data we collect is some combination of multiple of these. So we are going to be working with these models, is why we've been spending a lot of time introducing them. It's just that we're not going to be working with them in the classic way. So in the classic way, you treat your data as having no observation error. Mark, reference this where, they use it for like, think of like a stock price. Well, that is the actual stock price. It's not that you don't know what it is. But it's really different for us. If we go out, we're measuring like fish in a stream. There are so many reasons why that's not the total number of fish out there, either in that location or just, the whole population, obviously. All right. So that's one thing. So yes, we are working with these. We just it's kind of a layer removed once we get into observation error models. So that's one thing. And then the second thing, as I said, is that these models actually do really well if your objective is to forecast things. And in the future, you're likely to get into a situation where you want to forecast something. So you should know about how to do things the classic way, and to be able to use this as a null model against which you're going to be testing more complicated models. So, I had a quip that I used to say, because my specialty is in forecasting and in modeling populations, people would ask me, yeah, Eli, what's a good, can you come up with a good, we need a forecast for next year or next season or next month. I'm like, yeah, I can give you a good forecast. What was the last value you observed? That's my forecast. And I'll have a hard time beating that forecast, actually, unless it's really seasonal. And then I would use, what was the value if it's January, what was the value last January? That's my forecast. And that's actually a pretty good forecast in many cases. But the other thing is that in the classic model, it looks like this. Here is your AR process. And in your AR process, you have the data today, what you observed today, is some function of the past. This is yesterday, and this is P days in the past. So it's some function of that. And in the classic approach, this is just some error that you don't really care about. And in ecological settings, we really care about that. And we want to understand what is driving that, because we think of this as not some random thing. We think of this as something that's being driven by something. Maybe it's something we do, a perturbation. We go out there, we get a bunch of fish, or some pollution gets dumped in the ocean, something like that. Or we think of it as driven by some environmental variables, and we want to understand that. And these classic models won't allow us to ask that question. So in the next, starting, I think it'll be 3 weeks, three lectures, we'll start getting at answering that question. All right. So, but let's back up. Let's talk about the classic models, which are used for forecasting. And I'm going to be talking about ARIMA. So Mark, the last lecture, talked about ARMA. And now we're adding a letter I in the middle there. So now it's ARIMA. That I stands for the word integrated. But what it means is that we difference the data, we difference the time series, which means we subtract, say, the value today with the value yesterday from the value today. So that's a first order difference. So that would be differencing, first order differencing. So we do this differencing, and we are doing that in order to get rid of non-stationarity. So we might do it to get rid of a linear trend. We're going to see a bunch of different kinds of trends that we would use the differencing to get rid of. And the reason we're doing this is that when we get to this next step and we're fitting these ARMA models, we want to fit those models to stationary data. And there's a really fascinating theorem that shows that if you take a time series and you just keep taking differences, eventually you will get to something that is stationary. So if we take our time series, kind of whatever it is, and we take enough differences, we can eventually get to something stationary, and that thing could be modeled by a ARMA process. So that's what we're doing. We're differencing to get to this stationary time series, not going up or down. The variance isn't blowing up on us, anything like that. And then after that, so once we've got that thing, which we're going to call Z, our difference data, then we're going to model that as some function of the past. And it's a particular kind of function. It's an additive function. So it's not multiplicative. It's not like yesterday times 2 days previous. It's yesterday times a constant plus another constant times 2 days prior, that sort of thing. So it's an additive relationship. We have some error there. And then, so that's kind of our autoregressive part. And then we have this moving average part, which is modeling what is this? And it's saying, hey, is that error independent, temporally independent, uncorrelated? So whatever my error is, like whether it's a really hot day today, unusually hot today, it's not correlated with what happened yesterday. So if yesterday was unusually hot, that doesn't tell me anything about whether today will be unusually hot. If you think about that, you would say, oh, that's probably not true. So like something like temperature, it might be that the errors are correlated. And this would model correlated error. Okay, so that's what ARIMA is. So how do we go about fitting these models? So first thing that we do is this part. This is your selection. So the first step is you need to figure out how much differencing you need to do to get to stationarity. So you have to have tests that you can do to formally test whether whether A, is differencing needed at all, and then B, how much differencing do you need to get to stationarity. And then you're going to fix that by selecting how much differencing you do. Once you have something that's stationary, then you get to go to these next steps. You're going to select the how much it depends on the past, and then you're going to select whether or not the errors are autocorrelated. And only once you do that, you have the structure of the model, then you can go to the parameter estimation part. And the parameter estimation part is estimating these things here. But you're only going to do that after you have selected the structure. Okay. So When we get into the code, we're going to use the forecast package in R. It's going to automate a lot of these things. It's going to automate all of this for you, actually. And if you are dying to see more math in 2023, last time we taught this, I did a lot more math. I cut a lot of that out this time because I want to just focus on the concepts and not on showing the mathematical forms of things. Okay, so you saw things like this in the last lecture by Mark. This is an example of stationarity. This is white noise. That means we're just drawing from, in this case, drawing from a normal distribution and how far this is from zero. It has a zero mean. How far this time step has no impact on how far this one is going to be from zero. They're temporally independent. And if we do a whole bunch of these, it looks like that. It's just fluctuating around. It doesn't start wandering off anywhere. The variance doesn't start increasing. No, look, that variance is kind of steady. All right, so that's characteristic of stationarity. Now, that was white noise. So that was autocorrelate. That was temporally uncorrelated. But we can have things that are correlated. So this is a time series that's correlated. This phi is less than 1 and greater than -1. So as Mark was talking about last lecture, that's a stationary process. We look at it here, we can see kind of visually that it looks a bit autocorrelated. It looks different than that white noise. It is autocorrelated, but if we simulate a bunch of these, we see it doesn't start exploding off. It stays within a band. Characteristic of stationarity. Yeah.
So for AR models, if the phi is beyond that range, so that will be non-stationary. So
yes.
Can we like turn the non-stationary into stationary by difference?
Yes. Yes. That's what you would do. You would keep differencing until you achieve a stationary model.
Okay. So my understanding for like the AR model stationary is because of the phi, like the value of the phi, which like can approximate to like an model, like infinity those steps. But if the phi is like the value of the phi is not within that range, we cannot approximate that process.
Right, but we're not going to model that data. So if that, say that phi is equal to 1, so we have a random walk, as you'll see in a moment. I think I still have the math up there. If we take the first difference of that, that becomes white noise, which is stationary. We can do the same with other types. I mean, I don't know, like if it's too pathological, it might not, but theoretically, if you do enough differencing, you will eventually get to something stationary. In practice, in real data, usually you don't need more than 2 differences. Did you want to say something?
I mean, I think maybe you covered this, but I think like the first differencing process for anything that's non-stationary will make things stationary with respect to the mean.
Mm-hmm.
And then it's the other differencing that you would need if you had like wild pulses in the variance, for example, for a time series, and if there was a trend. The first differencing would remove the trend, but it wouldn't. There would still be non-stationarity with respect to the variance throughout the time series, and you would need to do the iterative differencing. I don't know how many times. I've never actually seen that in practice, but you would have to do that presumably a lot of times to get that to be something so that the variance is constant too.
So like if you difference it first and then you difference again, it's different than like just do like the second order difference.
That would be what you just described would be a second order difference. You take the first difference and then you take the difference of the differences. That would be the second order. All right, so here are some other examples of non-stationarity. So both of these are stationary. They don't have a trend and they're fluctuating around 0. So we might have a non-zero mean. And that's, although that's not, that's not technically non-stationarity, that is something that you get rid of, either, not by differencing, but you would get rid of it by removing that mean. You take that out. Here would be your classic thing you're going to get rid of with differencing. This linear trend can also have a linear trend there. You need to get rid of that. But if you think about it, if you kind of look at this, you can see that it's not this linear trend, but it's just fluctuating around that linear trend. So here, it's fluctuating. So this is a type of stationarity. I think I might have, said that kind of incorrectly when I was describing this from the beginning. So these are all stationary. It's just that, like, this has a trend. So you think, oh, that's not stationary because it has a trend. But the fundamental process here, the wiggly part, it is wiggling around a linear trend. And we can easily get rid of that linear trend. It's different, fundamentally different than if this were a random walk. This is more like just like a straight line here, and then we plot white noise on top of that. And then this one, kind of same idea. It's a straight line here, and we've plopped this stationary AR1 process on it. Yeah?
So would we be able to difference to stationarity if we had something that was wiggling around a trend that's not just linear, but like maybe going to different states repeatedly? Like, how complicated can the underlying trend be?
Yeah. Yeah, so it can't be all that complicated. It can be linear, like to just get rid of it with differencing.
Yeah.
It's going to be linear, or it's going to be, I'll show a picture in a moment. It can be like an exponential thing too. Get rid of that. But if it's really funky, like it's here, and then it's here, and then it's here, you're going to have to take some different approaches to get rid of that. So maybe you need to have a model of your mean. And so that's where you get into one of these situations where you're thinking of the underlying process as some stationary thing, but then you are observing that with something else layered on top of it. In this case, you have the mean is being shifted different times. Yeah. Okay. So what about non-stationarity? So here's a random walk, just a simple random walk. And this is what it looks like visually if I do a whole bunch of these. And you see that the variance is increasing. It also kind of has these characteristic look. So this is white noise. So random walk's never going to look like that. And like this one's a bit hard. This is, getting kind of close to random walkish. You can't really tell until you simulate a whole bunch of these. But this, you see how it's a bit smoother. It doesn't have this tendency to keep returning to some mean value. So we can also have trends with these. And so this is our random walk. It looks like it has a trend, but it actually doesn't. This was just by chance that is kind of looking like that. Here, I have actually added a trend to it. So let's see here. Doing this at time t equals this. This is my trend. It's this thing here plus whatever it is, the previous time step plus some error. Okay, so I've added that, and if I add that to that equation, it will start going up like that. So if I took this doesn't have that mu term. If I simulated this over and over again, it would start spreading out, but if I took the average of hundreds of these, the average would be 0. Whereas if I simulated this over and over again and I took the average is going to be moving up with time. Here, this would be a linear trend. And what would a linear trend look like? That would be if I added that in there. So it's not just mu, it's mu times t. And then it kind of goes up exponentially like that. These are all classic types of trends that can be added to random walks, and differencing can get rid of those things for us. All right. So testing for stationarity. So we want to have something that is in this class. And we're going to be differencing our data until we get a new data. So our new data is this differencing. We're going to keep doing that until we get to something that looks like this. And as I said in the beginning, we're doing that because the goal is to fit this stationary ARIMA model. So since we have a stationary model, we need to be fitting that to stationary data. But what if we weren't doing that? So there are a lot of reasons why you're going to evaluate stationarity in your data for other reasons. And I just want to kind of mention those, because once we leave these, stationarity is still important. One is that the algorithm you're fitting might assume stationarity. It's a pretty common assumption. So you want to look at it and see, well, do my data meet that assumption? And this second one is like a really common one that comes up, is that somebody will be fitting a model that is fundamentally stationary. They might not recognize that it is. They might just think of that, oh, I have this complicated model. It can do all these complicated things. But if they were to simulate from that model thousands of times and they looked at the data, they would see that it does this, that the variance is constrained and the mean is flat. But if they were to plot out their data, they might see that their data tends to go up or their data tends to explode. And so their data is inconsistent with the underlying model. So it's just whenever you are doing any kind of statistical analysis, you need to step back and say, think to yourself, could these data have come from that model? And the easiest way to do it is like simulate your model, make some fake data and see if your model can produce data that looks anything like what your actual data are. All right, so how do we test for stationarity? The first thing we do is we just plot our data. So, and that will often make it obvious whether or not the data are stationary. So you're looking for change in the level over time, like the mean, and the change in the variance. So let's look at some real data. All right. So looking at this, I would say, I can't say that's not stationary. Looks like that definitely could be. This one, I would be rather concerned. Feels to me that that probably has a trend to it. And it looks to me like it keeps getting pulled back, like it goes up and then it's pulled back down, up and then it's pulled back down. And random walks don't really do that. So a random walk can definitely have, just by chance, a trend. Watch this. So here, this was just by chance. It doesn't have that kind of like saw shape that we see in this data. So here I'm like, I think that's problematic. So that's just like a visual test. Often that will pick things out. Or another thing is I would be asking, hey, what's the mean look like? Okay, that mean is definitely not zero. So clearly I need to demean the data. That's obvious. That is not zero. That's not zero either. Okay, so the visual test can reveal a lot. And then the next one is, like if you're, when you're using the forecast package and it is figuring out how much differencing you need, it's going to be doing these two tests. So these are the two classic tests. This is the augmented Dickey-Fuller, and this is the KPSS. And those are four people's last names that are very long. So both of these tests, or the Dickey-Fuller test is testing for what's called a unit root, which is a random walk. It's another name for a random walk. It has to do with that in an autoregressive, that phi, if you set it to 1, it's a random walk, so call it a unit. Well, it's related to that, let's just say that. Anyhow, so you're testing for a random walk in the data. And you're trying to reject the null hypothesis. So the null hypothesis is that the data have this random walk in it. And we saw in the, in this one here, let's go back here, okay. So like this is still a random walk. It's a random walk with a trend. And this one is a random walk with a trend that's increasing at each time step. So both of those would qualify as having a random walk. So our Dickey-Fuller is testing for things like that. And it will do things like remove that. So we'll look at the data, and then it will, the augmented part is removing those trends and then re-looking at whether or not there's, if we remove the trend, if it has a random walk to it. And this one is testing, it's a different type of test for stationarity. And this one is like the default typically, and then you confirm with that one typically. Again, the forecast package is going to automate that for you. All right, so let's see, speaking of the forecast package, how does that work? So we load the library, the forecast package, and it's this function called indiffs, which says how many differences do you need for the time series to be stationary? And you can specify which test that it uses, do question mark indiffs and R, and it'll tell you about that. So it's pretty easy. Just do indiffs and forecast. It'll run both those. You can try both the test and see, does it pass one of them and not the other? If you've run into that situation where like it passes the Dickey-Fuller but not the KPSS, then it's sort of like, well, it's sort of borderline. You might want to do another, if you're really concerned, you might want to do a second difference and be like absolutely sure. Okay, fixing the stationarity problem, use differencing. And so, do I have that here? Yeah, okay, here, I'll show you an example. So, use diff. If this is your time series, you use diff. It does that first difference for you. So first difference is this minus that. And then the second difference is you take the diff of the diff. So you're going to take ZT, which is these two differences, ZT minus 1. That's it. So when you're okay. Yeah, so here's your example here, doing these different tests. And what it's doing here is it's taking that anchovy data that I plotted and it's applying the KPSS test. And what is it telling us? It's telling us that we need to do one difference to get to stationarity. And do it with this test, and it's the same. And that is getting rid of this trend for us. So that one difference is getting rid of that trend. And you can see that here. So this is the plot of the original data. If I take the first difference, aha, there, it looks stationary. It's kind of flat. Okay, so test for stationarity before you fit a model. Just in general, when you're working with a time series model, you're always going to plot your data and take a look at it. And then you can apply these standard tests for stationarities. Just do this with the in-diff. It's the easiest way to do it. However, the visual test is kind of going to tell you if the differencing is going to work. And you're looking for things kind of like in your example here, like what if you have it here and it's going up here and it looks kind of funky. Like if something's like you feel like, is that really going to work? Or maybe the data look like really sinusoidal, or they've got something like that. Like you might be a little bit suspicious if differencing is going to work. And so you could difference your data, do a first difference, and then run one of these tests on the first difference and see what it comes out with. Or you plot that first difference and kind of get a feel for whether the differencing is actually getting you to something that looks kind of like that. All right. Okay, so you've gone there, you've got that. And then the next part is, okay, so you settled on the differencing. The next part is selection of the autoregressive part and the moving average part. So Mark talked about using the ACF and the PACF, and definitely you should do that to understand your time series in the lab. We ask you to do that on the time series you'll be looking at. However, in practice, when you are selecting these models, the way it's done in the final analysis is via model selection criteria. So in the forecast package, you could use AIC, AICC, which is one corrected for short time series, or VIC. And these model selection criteria, basically they're weighing how well does a model fit the data, and then penalize for how many parameters that you're estimating. So if you estimate a whole bunch of parameters, you can fit the data really well, but you really should like penalize yourself because you like had so many parameters. And that's what these are doing. They're penalizing that. And the auto ARIMA is doing all this for you. So what it's doing is, well, you'll see in just a second. So let's see here. Okay, great. So first, let's just see how it works. So I'm going to take my anchovy data, and it's a time series. I'm going to put it into the forecast auto ARIMA, and it's going to spit out this. So what does that mean? This is the amount of auto regression. This is the amount of differencing. And this is the amount of moving average. So basically what it's saying is that this is, we can model the first difference as the first difference with some autocorrelated error. Very simple model. I'm just going to take the first difference of that anchovy data, and then let's write this. I think I have that. No, I don't. Okay. So it's going to be ZT, which is XT minus 1. So that's the difference. Equals. So there's nothing here. 0. So it is this error. But this is autocorrelated. So it's not exactly like white noise. It doesn't like it doesn't have like zero information. It has a little bit of information. So it says that the error today is correlated with the error yesterday. So if I knew how unusually high the anchovy count was relative to the mean, if I knew that from yesterday, I could tell you something about today, because that yesterday amount would give me some information. Yeah.
How do you know it's autocorrelated?
So it's right here.
Because it's the MA1 model.
Yeah, MA1. So what does that mean? So MA1 is, okay, let's say that ET is normal 0. Yeah, that's white noise. This is white noise. White noise is uncorrelated. And MA, moving average, is ET equals this white noise plus some theta times ET minus 1. So this is the autocorrelation part. So the error that I observed today, we've got some random error, so white noise, plus what the error was yesterday. So if I knew what yesterday was, I have a little bit of information about what the error is going to be today. So whenever you see a number in this part, it's telling you that the error term, that random variability, is correlated. It doesn't actually, so here you have 0. So the difference, the first difference, does not depend on the first difference in the previous time step. This is 0. It's not auto-regressive. But how much error there is, how much fluctuation, that fluctuation is not white noise. It's a little bit, well, it could be a lot autocorrelated. Yeah.
Can you explain the coefficient, or we're just not there yet? The coefficient.
The coefficient. Yes. Okay. So, yeah. Okay. So the drift term is a mean. The terminology here is really painful. There's kind of a historical reason why that's called drift. As a practical advice, when you're using the forecast, like in the lab, you're going to get it, saying what the model is. It's really helpful to use AI for this. Like, have your whatever, like, AI thing that you like, have it open, copy that and say, tell me what this is, describe this, explain this to me. And it will do a really good job with explaining what this is. Because for certain types of model, drift might mean a linear trend, and then others, it's going to be a change in the mean. All right, so that's what this is. What it's saying is that if we look at the first difference, let's do it here. Kind of see this. Okay, so this is the first difference. It's not very much above 0, but what it's saying is that the mean of this is a little bit above 0. And then the second thing that it said is that this term here was negative. And do you kind of see that? What it's saying is if the last step, if this was really positive, the next one is going to tend to be negative. If this is positive, the next one's going to tend to be negative. And that is what this is saying. Because this is this term right here. Saying if that yesterday was really positive, then it's going to have a negative impact on today. So it's going to tend to come down. So if you see something that looks like this, definitely this term is going to be negative. Great question. Okay. So what did ARIMA do for us? What it did for us is it fit a whole bunch of different ARIMA models. And these are the ones that it fit for us. This suite of them. You notice, hey, why is this always 1? Because it makes that decision about how much differencing to do beforehand. It's going to make a decision about how much differencing to make it stationary, and it's going to keep it difference at that value. So that's never going to change. What it's going to vary is, first off, the amount of autocorrelation in the error, so the MA term. This would say that the error yesterday has an impact. This one would say that the error yesterday and the day before yesterday matter. This is the autocorrelation part. Here it's saying what the actual value was yesterday doesn't matter. This one says yes, it does. And this one says the previous 2 days matter. So it's going to compare these different structures. It's going to fit these models to the data. And it's going to compute, I believe it's AICC, is the model selection criteria. So it's going to compute that. So it is based on how well does it fit the data, and then it's going to penalize based on how many parameters it's estimating. So here we have 2, 3, 4, for example. More negative is better. So this is the most negative one. That's why it shows us that. Okay. So let's see here. Okay, good. Great. So let's fit to some simulated data where we know what the answer is. This is a simulation function. It's, I believe, in base R. So we're saying, hey, simulate from a ARIMA model. And here's the model that I want you to simulate. I want you to give me 100 time steps. And I'm going to give, I'm not going to pass in moving average, so there's no autocorrelated noise. But I'm going to say the AR components are 0.8 and 0.1. So what is that model? Let me go right over here. So model is xt equals, what did I say, 0.8? 0.8 xt minus 1 plus, there, 0.1 xt minus 2, and then plus xt white noise, because I said there's no moving average component. If you do like question mark ARIMA sim, you can see the other things you could specify. You can specify, for example, the moving average part, and you can specify the variance of that white noise also. But I just went with the default here. So I simulated that data. That is a one-time series. So A1 is just one time series with 100 time steps, lots of information. And I'm going to use auto ARIMA. I'm going to make it a little easier for auto ARIMA. I am going to say, hey, auto ARIMA, don't monkey with D. I know that D is equal to 0 because I'm simulating from ARIMA. You don't need to, I know I don't need to difference it. So I'm going to give it a little information. Don't change the D. And then I also know it's not seasonal data. So I'm going to say, hey, seasonal is false. I want it just to try to figure out the structure. I want to see, is it going to pick an AR2 or is it going to pick something else? So this is a little for loop. Run it 100 times and let's see what it does. So nice. It didn't, so this is the AR part and this is the MA part. Yay, it figured out that it didn't have autocorrelated noise. It did really well with that. This was true. This is 2. Should have been AR2. So remember it was that 0.8 and 0.1. But it most of the time it picked a simpler model. This is not an unusual result, that it is choosing a little bit simpler model than the true data. It can be hard to estimate these parameters, that second that 0.1, that can be hard to analyze, hard to estimate. I would bet, well, at some point, like I did 100 time steps, at some point, like if I went up to 200 or 300, at some point it would start to be able to estimate that second one and say, oh, okay, I've got enough information. I can distinguish that. That's a better model. So last nice thing to know about auto ARIMA is when you get to the final step, you can tell it to do a larger set of models and do kind of an exhaustive search. So if you set it this way, it will take a bit longer, but it'll do a more exhaustive search of all the space of models. Okay. Model checking. So you fit your model. Hey, boom, you got that with ARIMA. You know, we just spent like a long time talking about this, but actually when you fit the model, it's going to go like that. And now once you have your model checking. And standard, any kind of statistical analysis, we're going to be checking the residuals. What is the residual? It's the difference between the data and the prediction. So if you had an AR2 model, which would look like this, your prediction would be everything except the error. And your residuals are going to be the data minus this prediction from the model. So you're always going to be looking at that. And a nice thing in R is like the residuals functions exist for all kinds of different types of fitted objects. So and it's the same in forecast. If you just say residual to your fit, it's going to give you the residuals. You can plot those. But and you can get the fitted also. Again, another really standard function in R for getting fitted values. And a really nice thing in the forecast is it will show you the standard things that you do with residuals. So once you get your fit, run check residuals. And what do you do with them? You plot them. So number one thing. Then you take them and you run them through ACF and you see if they're autocorrelated. They should not be autocorrelated. That looks good. And then for this model, they should look fairly normal. Okay, I'd say that's close enough. What would be bad? Well, like bimodal. Bimodal would be bad, you know, or something that looks kind of like that. All right. That's the test if you actually need to report the autocorrelation test. It's a little non-intuitive that you have to put plot equals false, and then it spits out this information for you. Yeah.
So for the residuals, I mean, this isn't the case, but maybe going forward, right? We know the ecological data.
Yeah.
And it's pretty messy, like how bad does, or like how good does that have to be, if that makes sense for residuals? Like this is a pretty nice result, but how do you draw the line between, you know, like residuals don't look normal enough versus, is there kind of a stepwise process for that, or is it? You know, like
Yeah.
you say this is okay, right, compared to a normal, but how bad would it have to be for it to pass it for?
So it would, I would say it's just going to really jump out at you that it looks bad. You know, Mark was showing some examples where, you know, it can happen that one of these is up. You know, think about, you know, how many tests you're doing. And so if just one of them is out, then you might be like, okay, that's okay. If you want something that is less hand wavy, then for sure, look up how to apply this to your residuals, and then you can do like, you know, the classic formal test for autocorrelation. And that will take into account how many of these tests that you were doing. When things look bad, well, if you look at your residuals and this one were up and that one were up and that one were up, and that doesn't happen by chance. So you'd be like, okay, there's some sort of cycle in my data and I have not accounted for that. If your residuals look like this, boom, 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 boom. So it's not just like one of these out, it's like a whole bunch of them up like that. And you're like, oh, okay, that's not good. That doesn't happen by chance. In terms of like this. The things that are really bad are going to jump out at you, like bimodal. That's really bad. And that, yeah, like something that doesn't even look remotely like it's got like a central peak. And that can definitely come up if, I guess one way I often see it is like if I'm working with binned data. It's like kind of a really classic example. Or if the data have been altered to make it quote unquote better, that can create residuals that look really odd. Yeah, you're going to see lots of odd residuals in this class. Real data has odd residuals. Yeah.
So after we have done this, like the code have already helped us diagnose it. Like if the residual look odd, like what's the way to fix it?
So you may need to detrend it in some way. So remove the cycle. So maybe you are going to let's say the data are really sinusoidal. It's clearly sinusoidal. You could do like seasonal differences, but another thing that people will do is like they fit that sinusoidal, they estimate that, and then they remove it. Something like that. Once we get into state space models, a really common approach is you model the underlying middle of the data with a random walk. And you are essentially removing that random walk, and you're modeling all the error that's moving around that random walk. So you say, all right, my mean is a random walk, and I'm just going to say that's what that is. But what I care about is I don't really care about the fact that the mean is moving like that. What I care about is how much is it up above that mean or below that mean, and I care about that. And that's what I'm trying to model, because I'm trying to understand is that happening because temperature, something like that?
I was saying like in the previous code we probably can turn on the seasonal, or is that what you mean?
Yeah, for the lab today, you'll be. I'm about to jump into seasonal stuff, and so I'll show you how to do that. Yep.
Yeah, I mean, it's also conceivable that you just have something like a very heavy tail distribution, so they're not actually Gaussian errors.
Mm-hmm.
So this, when we start looking at like QQ
Yeah.
plots, that happens every single year, and probably for 99 out of 100 projects I work on with folks.
Mm-hmm.
You look at a QQ plot, and the tails of that distribution are clearly deviated from the one-to-one line, and so you think, oh, those are not normally distributed.
Mm-hmm.
The standard
Yeah.
approach there is usually close enough. Yeah. I mean, literally, that's often the way it is. Or you move to something that would accommodate, a heavier tail distribution or something like that. So rather than Gaussian errors.
I think that's
Some-
maybe what my question was more about. How
okay.
many iterations, right? So, like in my case, and the QQ plots, exactly, the tails are off, and I show it to one person, they're like, that's horrendous, and another person who works with ecology data is like, that was great.
Yes. Yeah.
How many steps of troubleshooting like that do you do before you say kind of, I did good enough and I'm just going to give up and move on? Or do you say, no, I can't follow this? That's kind of I don't have that intuition.
Yeah, Eric, can you chime in? My feeling is that violations of those assumptions in that case are kind of minor consequence. What is it? You're not truly capturing all the variance of the tails. So maybe if you're dealing with a lot of extreme values and that tail is super important to you, then you would want to think about that. But otherwise, like I said, a lot of it's like, okay, I check the box on 9 out of 10 of my assumptions, the tails are okay. The flip side is ask whoever that was, yours.
Yeah.
I mean, it always looks good on paper, the example, but in practice, I see that quite a lot. Same later, we'll see. You put in all this stuff, you put in all kinds of covariates, and you look at your things, and there's still a little bit of autocorrelation in there. You think, well, so just change that line on your assumptions so that the variance or the mean is not 0; it's somewhat autocorrelated.
Yeah, I think that if I were doing this in a work situation, I would be using cross-validation, and I would test whether changing the error structure, the assumptions about the error, so using an error model that is closer to what I'm seeing in the data, I would look at, does that improve whatever I'm trying to do, or does it affect my inference? And so I'd be doing like simulations and cross-validation to test that. And so like if I'm writing a paper, to justify that that this deviation from my assumed normality is like okay, I'd have a cross-validation section in my paper.
That helps a lot. That helps a lot.
Yeah. Okay, so now we are going to hop into forecasting. So let's go. Yes, please. Okay, now we're going to take a break, everyone. We'll go into part 2 in just a moment. And then we'll have a longer break before we jump into the lab. All righty. Now let's get to the fun part, starting to forecast. So the concept behind forecasting is super simple. I'm not going to spend much time on this. Once we have estimated this model, we are essentially doing a bunch of algebra. I think I have it on the next one. Yeah. We are, so the part that the algebra comes in where we have these differences. And so we need to convert back from the differences from, the z's, which is what our model is for the z's. So it's really easy to get our forecast for the z's, but we then need to do a whole bunch of algebra to convert back to the data to make our forecast for the data. It's not hard. It's exceedingly tedious. Fortunately, it's super easy to program that in, and Forecast will do that for you. So here's an example. I am telling Forecast to fit a specific ARIMA model. Before I was doing auto ARIMA, I said, hey, Forecast package, why don't you select the model for me? Tell me which one is best. And with the ARIMA function, I'm saying, hey, no, don't decide what to do. I am going to tell you what model I want you to use to fit to the data. And all I want you to do is to estimate the parameters. So I'm telling it, hey, it's going to be a second order autoregressive. So it's going to estimate 2 terms here. So this is your first AR term. This is the second one. So estimate both of those. And I am telling it that I'm modeling first differences. And I'm saying, hey, yes, it might have a trend to it, which when you look at the first differences, it would be a mean. So I'm just telling it that, yeah, so hey, fit that model. So it fits that model and it returns the fit. You can look at what it was estimating. If you look at the coefficient, and yeah, and if you actually wanted to get what that trend was, there's a little bit of algebra there. Typically, we're not really concerned about pulling out the trend from this mean. Yeah.
If auto ARIMA is going to get to the same answer, what is the benefit of providing it with what you expect the models to be?
So you'll see in the lab that we'll be asking you questions, or like a question you could ask is a model, when I'm forecasting, is it better to use 0, 1, 2, 3, 4, like how much autocorrelation into the past is better? And I want to compare using different amounts of dependency on the past. So like in the real world, if we're looking at like an autocorrelated time series, there's probably multiple layers of autocorrelation. But estimating all those parameters could lead to really awful forecasts. And if you wanted to formally ask that, you want to compare one where you depend only on yesterday versus 2 days versus 3 days, you're going to have to tell it, do this.
So auto ARIMA is not doing that in the background.
It is fitting lots of these for you. And it's giving you the model, the AICC, or whatever model selection criteria you tell it. So I think it's, if you did fit and then $ AIC or AICC, it should tell you what the AIC is. Right? So here's that hairy math, which you will thankfully not have to do. You would fit that model, and then you have to like go through, put all these differences in there, and then keep moving things around to come up with your, you start here, and then you're going to do a bunch of algebra, and you'll come up with your forecast for the next year. So that's what the forecast function is going to do for you. So it's automating all that calculation, and all you do is say forecast, give it your fit, and tell it how many steps forward you want to forecast, and it's going to come out and give you the point forecast. It's going to give you your prediction intervals. These are the 80%, this is the 95%. Very nice. And it's really great. It's got these handy little plots for you. So the output you can see here. So I take my forecast, I assign it to an object, and then I just say plot. And it does that nice plot for me. I think it's auto plot to get some something that looks like it came from ggplot, if you like that better. Another great thing about this is that it's fine with missing values. So we can take our data, and I'm going to throw in some missing data. So I take this, and I say points 10 and 11 are missing, and 20 and 21 are missing. I can take that, and I can still toss it into the exact same functions, and I can get a forecast. So even though I chopped out the middle, I'm still able to fit the model nicely and make a forecast. So if I want ARIMA to select it for me, I don't want to specify it. It looks exactly the same. I use ARIMA, and that's going to be my fit now. And I can do the same thing. I assign that to, I forecast with that, and I plot my forecast. Yeah.
So why does the plot result from the ARIMA look slightly different from the plot result from we gave it the specific the parameters?
Versus,
Oh, I see.
yeah, this one is autoregressive. This one is no autoregression. And so that's why that actually why that line looks like that. I think. Okay, great. So yeah.
Just trying to like wrap my head around some of this stuff conceptually. If there's no auto regression specified, then is that forecast just going to be linear? It's not going to move up and down, right? It's just going to be going according to the parameters that are estimated, or
yes, because this has drift.
okay.
And with a first difference, drift means linear, a linear trend. And so this term is that linear trend. And so it's going to be, the forecast is always going to be, whatever that linear trend is. And then we have this autocorrelated error. And so the size of that will change this, but it's not going to change this. Yeah, that's a good question. All right, so on Tuesday, I'll talk a little more about evaluating your forecast using the accuracy function. That's going to allow you to have a training set, and then you'll have a test set, and you'll compare the forecast to the test set, and I'll show you how to get like a variety of like standardized forecast performance metrics. Okay. But we'll do that on Tuesday. Now what I want to do is talk about seasonal models. So you're going to be playing with seasonal data in the lab. You'll be playing with commercial landing data of Chinook from the West Coast and Alaska. And if we plot that data, it looks like this. It doesn't have this big gap here, though. You'll see this is kind of an older plot. You'll see when we look at the lab, it's seasonal. But if you look at that, that is very clearly some seasonal data. This is monthly data that most definitely has a seasonal cycle to it. And so when we are fitting that kind of data, we want to take that seasonal cycle into account. And this class of model are called, I've never heard anyone say the word. I don't know if it's called ARIMA or SARIMA. It's probably ARIMA. The basic idea with this class of model is that you have your non-seasonal part. That's what we've been talking about the past hour. And then you have a seasonal part. Let's see here. And so you're going to be doing kind of things like this. So first off, you're going to be differencing to get rid of this seasonal cycle, because we need to get the stationarity. We need to have stationary data, and we need it to not be cycling like this. So we're going to be using seasonal differencing, where we take this point, let's say this is January, we're going to take this January and we're going to subtract that January. So that would be the data at this point minus the data 12 months earlier. And we're going to be modeling those differences. That would be a first order seasonal difference. Okay, so let's think about this differencing. If we did a first difference, just like that, what's that saying is we are modeling the monthly change. There's no seasonal effect in there. We don't need to account for seasonality. We're just going to model the monthly change. What if we instead were modeling this? So what that would say is we are modeling the seasonal change. We're modeling how January versus January last year, and then February versus February last year. We're modeling changes. We're not modeling the raw data, we're modeling these changes. And if we had a, let's see, this is a second order difference. We are modeling the, well, actually it's not second order. If we have both of these, what we are doing is we are modeling, it's like the seasonal rate of change. So this is January versus last January, but we're looking at, and this is February versus last February. And then we're saying, how is that changing? We're taking how the January to January is different from the February to February. And we're going to model that difference. Those are the three kind of classic differencing that we're going to run into in seasonal models. The notation for this class looks like this. This is the non-seasonal part, and this is the seasonal part. And then this is the seasonality. So if it's monthly, this would be 12. If it's quarterly, this would be 4, that kind of thing. If it were hourly, it'd be 24. Okay, so let's just see some examples. This is the non-seasonal part, and this is the seasonal part, and the 12 tells us that we're looking at monthly data. As I said before, instead of like trying to twist your head and remember all this, you copy that, throw it into your AI and say, hey, what is this? What am I looking at? Describe this for me. And that will really accelerate your learning rather than trying to remember or look up what the exact notation is. Okay, but let's break it down. So that's non-seasonal. This is the seasonal part. Does it have any differencing? No, it does not have any differencing. That means we are modeling the raw data, the data as they are. And we've got this. So it's saying this month depends on last month. That's what this is saying. This month depends on last month. January depends on February. Depends means if we knew what February was, it would tell us a little bit about what January is going to be. So it has that plus a seasonal part, plus the same month last year. So January is affected by February plus whatever January was last year. And in math, it looks like this. So there is no z, it's just x. We're not doing any differencing. This is that it depends on the previous time step, and it depends on the time step 12 months earlier. How do we know it's 12 months earlier? Because I told you what the season is, that we're looking at monthly data. All right. Let's look at this one, kind of break it down. Okay. So first, you start in the middle. What are we modeling? Well, 12, it's monthly data. We look here. What are we modeling? Aha. Okay. We've got a 1 here. That means we are modeling seasonal differences. That means January this year minus January last year. We're modeling the seasonal difference. And now once we know what we're modeling, now we can say, aha. So the seasonal difference this month, January, depends on the seasonal difference last month, or depends, or is affected by, or is correlated with, I guess correlated is the more accurate statement. It's correlated with the seasonal difference last month plus the seasonal difference the previous year in January. What about this one? Okay, we start in the middle. What are we modeling? I only have it here. So we're modeling seasonal differences. We're modeling January this year minus January last year. And everything else is 0. So it's just saying that whatever the value is, the seasonal difference this year is last year plus some random white noise. And if you kind of do the math here, what it's saying is that this month, so January this year, is January last year plus some noise. That's called a seasonal random walk. So you don't care what it was in February. You just say, what was it a year ago in January? Or February, whatever month you are this month. This is one where we have a seasonal difference and a monthly difference. So it looks like this. These are the seasonal difference this time step, the seasonal difference the previous time step, and then we take the difference of those. We're modeling that thing. I think yeah. This is a really classic model, and in fact, it has a name. It's called the airline model because it works well with, or there's this classic airline, it's passengers on airlines that they use this model for. And you can see it's got these differences. So they're modeling these seasonal differences, and there's no autoregression. All it has is these terms. So it's saying it's autocorrelated error. All right, let's see how to fit this in the forecast package. So the forecast package, the way that it works is that if you have seasonal data in the lab, you'll see how to create, how to tell R that it's a seasonal time series. You're telling it that it has a frequency to it. So you'd say if it's monthly, you'll say it has frequency 12. So that's how R knows that this is monthly data. So here I've split it into training data and testing data. I'm going to send the training data to ARIMA. And ARIMA will detect that this is seasonal data because it's got that frequency term. And it will test whether a seasonal model works. It won't necessarily use it, but it's going to test it as one of the options. And so in this case, what did it say? It said this is the best model. So it's saying we're going to use seasonal differences. So we're going to model January this year minus January last year, February this year minus February last year. That's what we're modeling. And it is a random walk. That thing is a random walk. Okay, let's see an example of forecasting with this. This is when it gets really fun. So here's the data you'll be playing with in the lab. So like I said, It has some missing values here and there. It's okay. You can fit the missing values. It's very seasonal for sure. The missing values are fine. That's great. So we fit the model with our auto ARIMA. Let it go ahead and select the best model based on, like I said, I think it's using AICC. And here we go. So this is, we trained on all this data. And so once you, like you do this. So if you just, put your fit there, and then you can say, hey, forecast out 12 months, plot that forecast. It's going to plot this. And then this is its forecast. And we can add the points of our test data. And you can see for this one, it did really great. All right. Oh, and that's the end. Okay. All right. I am going to stop there. We'll take another 5-minute break and then get you guys going with, show you what the lab is. And you guys can start playing with that. I won't need to do much talking, so you guys can kind of sort of get to know who your partners will be, and then start kind of playing with the data and thinking about kinds of things you might want to do with the data. All right, let's take 5 minutes.